Hello everyone, I'm Nashrah Afroze from Georgia Tech, and today I'll be talking about how we can get wake-up free and reliable ready-to-go ferroelectric capacitors for high-temperature memory on logic applications. So, uh, memory on logic application is basically twofold. One is when HBMs or memories are stacked on top of GPU, and the other is when memories are added to the back end with front end logic. And in both cases, we have to deal with one common problem, which is thermal management. And that is what what we are going to talk about in this talk. So let's get started. The burning question that the semiconductor industry currently dealing with is, are memories keeping pace with compute? And the answer is clearly no, as you can see from this plot. The purple curve shows the explosive growth of the AI parameter sizes with the boom in AI, and you can see that the parameter size is getting doubled in every 2 months roughly. However, if you look into the memory trend represented by the blue curve here, we see that it's comparatively flat, meaning our memories are not keeping up with the pace of the parameter sizes, and this brings us to the memory and bandwidth limited era, where a memory wall is a great challenge, and only scalable and reliable memories can help us overcome this memory wall that we are having. Now, industries have been working hard to increase the capacity of memories, and uh, if we look into the DRAM side, DRAMs have gone from 2D to 3D architecture. So DRAM has been traditionally a 2D technology where the capacitor and transistor sit side by side. But now the industry is moving towards 3D DRAM architecture. Instead of only scaling laterally, capacitors and transistors are now stacked vertically, utilizing the third dimension. But this is still not enough, because you can see that after 2015, the areal density of memories of DRAMs has gone slightly saturated. And if we look into the capacity is increasing, but still we had a maximum of 8 GB DRAM capacity. But a major breakthrough happened when Micron showed 32 GB ferroelectric non-volatile DRAM architecture, where they showed a dual layer architecture. And what they did here is that they replaced their traditional capacitors in DRAM with ferroelectric capacitors. So this change makes it a non-volatile DRAM architecture, through which they were able to gain 32 GB capacity in their non-volatile DRAM. Now this brings me to introducing what ferroelectric material is. So ferroelectric material is an insulator with a spontaneous polarization, which can be switched by a voltage above coercive voltage. So traditionally, semiconductor industry is more familiar with perovskite structure ferroelectrics, but those have some issues. For example, those are not scalable and those are not CMOS compatible, and that's why fluoride structure ferroelectrics have caught attention in the recent decades. So it can be scalable, and it is CMOS compatible, which makes it far better useful for semiconductor industry. If we look into the traditional state-of-the-art memories, we see that there is a gap between DRAM and NAND. So we are still missing memories which will be denser than DRAM, but will have less access time compared to NAND. And this gap can be bridged using ferroelectric RAM or non-volatile DRAM architecture. But non-volatile DRAM or ferroelectric memories in general have a few disadvantages as well. It has some challenges. For example, one of the challenges wake-up effect, where we see that at the beginning we don't get enough polarization in our ferroelectric films, but we have to apply certain number of cycles to get a better polarization value and a proper ferroelectric switching current. And another challenge is reliability and endurance. So in ferroelectrics, uh, the ferroelectric material goes through both the bipolar switching and also the bipolar stress. So that's why the endurance and reliability is worse of our ferroelectric materials compared to conventional dielectrics, where only stress plays a role. So now, when Micron demonstrated their non-volatile DRAM, they have of course solved a lot of these issues. But what's next? Like if we look into the semiconductor memory industry now, we see that the HBMs are placed on the side of GPU. But if we look into the recent trend in semiconductor industry, the recent trend is memory on logic architecture, where uh, memories are stacked directly on GPU or CPU. But we have a huge thermal management issue over here, because according to depending on the chip activity, when the CPU or GPU gets heated, that heat will get transmitted to the backend memories as well. So our memories not only have to be reliable at room temperature, but also we need reliability of our memories at higher temperatures for memory and logic applications. And here we have to deal with temperature above hundreds, because the logic dies are qualified to operate at 105 to 125 degrees Celsius based on its activity. And then um, if we look into the DRAM qualification temperatures, those are 85 to 125 degrees Celsius, depending on its application. But DRAMs don't like heat in general, because above 85C, for every 10 degrees Celsius increase in temperature, the refresh rate has to be doubled in DRAM. And also off current scenario becomes worse. So these are the reasons why ferroelectric memories are better candidate or has a better prospect for memory and logic applications, because even at higher temperature we won't need any refresh cycle, and we don't have to worry about off current situation for ferroelectric RAMs or non-volatile DRAM. But if we look into the performance of ferroelectric memories at higher temperature, those are also not very good at initial case. So for example, you can see that so in this plot, we can see that the green curve is coming from room temperature measurement, and the red one is coming from high temperature measurement. And you can see that as soon as we're going to higher temperature, we're getting more and more pinch loop, and we're getting more and more double peak behavior in our switching current. And not only wake up issue gets worse, but also endurance gets worse as well at higher temperature. So you can see in this plot, the x-axis is temperature and the y-axis is number of cycles before breakdown or endurance of the devices. And you can see as we are increasing the operating temperature, the endurance degrades very fast. And this phenomena is true for other thicknesses of our ferroelectric film as well. Now, what if I tell you that we can solve both the wake-up problem and the endurance problem at higher temperature in ferroelectric memories by using one simple solution, and which is using plasma enhanced ALD deposited HZO films. So let me go into what I mean by that. So let me first describe the fabrication process of the devices that we are using in this study. So we are basically comparing thermal ALD sample and plasma ALD sample. So on both of them, we start with sputtering tungsten bottom electrode on silicon substrate, and then we deposit 5 nanometer hafnium zirconium oxide ferroelectric film. Now, the difference between these two is in thermal ALD, we use water as oxidant in the ALD process, and in plasma ALD process, what we use is we use oxygen plasma as the oxidant in the ALD process. So this is the only difference between these two devices. Next, we deposit we sputter the top tungsten electrode to get the capacitor-like structure. Now, if we look into the TM of both the devices, we can see that we are able to get 5 nanometer HZO film sandwiched between top and bottom electrode. But what's different is that in plasma ALD film, we are getting some unintentional tungsten oxide layer at the bottom interface, because Plasma ALD process is a high power process. So while depositing the HZO layer, we are unintentionally oxidizing some portion of the bottom tungsten electrode here. Next, we have done the standard characterization of our HZO film of both the thermal ALD and plasma ALD devices. What we are seeing is that plasma ALD is having higher orthorhombic phase compared to thermal ALD process. And this phenomena is also recorded in the electrical measurements as well. So these are the PV loops coming from thermal ALD and plasma ALD device. Measured at pristine state at 25 degrees Celsius, and what we are seeing is that we are seeing the same trend, that the polarization of the plasma ALD device is better compared to the thermal ALD device. Now this was at room temperature. Now let's see what happens when we go to higher temperature. So these plots are coming from the thermal ALD device, and you can see that we have measured it from 25 to 105 degrees Celsius temperatures. Now, as soon as we are entering into high temperature operation regime, what we see is that our PV loops of this device are getting more and more pinched. And if we look into the current characteristics, we are seeing more prominent double peak behavior, which shows an anti-ferroelectric behavior at higher temperatures. Now, if we look into our plasma ALD device, we are seeing something completely different. What we are seeing here is that starting from 25 to 105 degrees Celsius, we don't see any significant pinching in our hysteresis loops, and also we don't see any double peak in our switching current as well. What does it tell us? It tells us that even at higher temperature till 105 or 125 degrees Celsius, the plasma ALD device is able to maintain its wake up free behavior, and it doesn't need any wake up cycles, or it doesn't need any cycling to get proper hysteresis and proper ferroelectric switching, because we're already having it in our pristine state. Now, since thermal ALD has a wake up issue, so we have to cycle it for getting proper ferroelectric behavior and for waking it up. And this is the bipolar pulse scheme that we have used for waking up our devices, and also to study the endurance. So what we are doing is we are applying 200 nanosecond bipolar cycles, and we have applied pulses of different amplitudes from 1.6 to 2 volts. So for waking up and for also endurance measurement, what we do is we measure the PV loop at pristine state, and then we keep cycling and measure the PV after different amount of cycles until the samples break. So, and the cycles that our devices can endure before breakdown, we call it endurance of our device. Now let's see that how many cycles are needed for thermal ALD for waking it up. So what we saw is that after 10 to the power 5 cycles, so at these are the curves coming from 105 degrees Celsius, and what we are seeing is that at pristine state we were having pinch loop, we were having double peak in our current, but after 10 to the power 5 cycles, what we are seeing is that we are able to get a proper ferroelectric loop, and also we could remove the double hysteresis in our current. So this tells us that 10 to the power 5 cycles are necessary to wake these devices which are thermal ALD deposited. Now you have already seen that the plasma ALD devices don't need any wake up cycles. So this is the PV loop and IV characteristics at pristine state, and this is after 10 to the power 5 cycles. So we see a reduction in 2PR, but we don't see any wake up effect after 10 to the power 5 cycles. Now we have tried to understand that how much polarization is increasing after cycling in both of these devices. So here the x-axis is temperature, and the y-axis is the difference of 2PR, or the difference of polarization before and after 10 to the power 5 cycles with respect to the pristine state. So this will tell us that how much polarization we are increasing after 10 to the power 5 cycles compared to pristine state. And this also is a measure of the wake-up effect of both the devices. Now, at room temperature, what we see is that both the devices were having similar polarization change. However, as soon as we're going to higher temperature, the plasma ALD device is able to, it doesn't show any significant increase in polarization. However, if we look into the thermal ALD curve, we see that a significant increase in polarization is seen when thermal ALD sample is used. So this means that the thermal ALD sample is having more prominent wake-up effect compared to plasma ALD over a wide range of temperature. Now let's see that how the endurance of both of these samples look like, and if we can get better performance on the endurance side when we are using the plasma ALD HZO. So we have measured the endurance of both the devices. So the top panel is coming from the thermal ALD device and the bottom panel is coming from the plasma ALD device. So you can see that at 25 degrees Celsius for 1.8 volt application of bipolar pulses, we see that we don't see any breakdown in our plasma ALD device. And this difference in endurance is more prominent at 85 and 105 degrees Celsius. What we are seeing is that thermal ALD device is breaking faster compared to the plasma ALD device in both the temperatures. Now, and we have measured multiple devices in each case here. So next we have tried to summarize the endurance data that I was showing in the previous slide. So here you can see that the x-axis is temperature and the y-axis is cycles to breakdown or endurance. So what we're seeing is that as soon as we're entering higher temperature, the thermal ALD device is showing worse endurance. However, we are getting enhanced endurance in our plasma ALD device at a wide range of temperature, and we are getting an enhancement of endurance of up to 2 orders of magnitude at 125 degrees Celsius. Now, why I mentioned 125 degrees Celsius? Because according to JEDEC standard, for 3D IC integration, memories have to be reliable at 125 degrees Celsius. Next, we have fed these cycles to breakdown versus temperature data into Arrhenius model, which is shown here on the top. And when we fit the data, the slope of this straight line will give us effective activation energy, which is a measure of how much temperature dependent degradation we are having in each devices. So the less the effective activation energy is, the suppressed temperature dependent degradation will be. So here we see that in plasma ALD device we are having lower effective activation energy compared to the thermal ALD sample. What this tells us is that in our plasma ALD device we are having suppressed temperature dependent degradation. Now, let me take you back to the TM images that I was showing in the first part of my talk. So you remember that we had a tungsten oxide layer at the bottom interface in the plasma ALD device. Now we wanted to decouple the effect of this tungsten oxide layer on the endurance and the effect that is coming from the plasma film itself. So for this, what we did is we intentionally grew tungsten oxide layer in one of our devices with thermal HZO deposition. What I mean is, I will show you the next slide. So we first start with our thermal ALD device, and we saw that the effective activation energy is 0.42 volt. Next, what we did is we intentionally deposited tungsten oxide at the bottom interface and then deposited the same thermal HZO film on this one. And here what we are seeing is that the effective activation energy was suppressed from 0.4 to 0.23 electron volt. Next, when we are studying the plasma ALD device, we see that the effective activation energy is further suppressed to 0.08 electron volt. So this is telling us that the suppression in temperature dependent accelerated breakdown, or uh, in the endurance that the enhancement in endurance that we're getting in our plasma device, that is actually coming from a combined effect of the tungsten oxide layer that we have at the bottom interface and also the plasma film itself. So we have extensively studied this tungsten oxide uh, sample where we have intentionally deposited it, and we published in an ITM. So if you scan this QR code, you can go to that publication if you are interested. So next we have done the endurance test at multiple voltages as well. So earlier I was showing the endurance test done at 1.8 volt. So we have also done at 2 volt a bipolar cycling and 2 volt polarization measurement. So what's interesting here is that you can see at 25 degrees Celsius for 2 volt application, the endurance was similar, but the changes are coming when we're going to higher temperature. At higher temperature, the plasma device is having better endurance compared to the thermal one. And same trend is seen in 1.6 volt measurements as well, that we are having better endurance in our plasma device compared to our thermal ALD device. We have tried to compare our plasma ALD device with some of the recent reports on ferroelectric capacitors, and we see that we are at pristine stage. We are getting better polarization compared to others, and we need 0 wake-up cycles at higher temperatures compared to other reports, where in other reports we see that at least 10 to the power 3 cycles are necessary at higher temperature, and we are also getting better endurance value compared to other reports at full switching condition. So if I have to summarize my whole talk, what I have been talking about is how we can improve the wake-up effect and also the endurance of our ferroelectric capacitors. And here we have used one simple solution. We have just replaced the thermal ALD deposition process of ferroelectric film with plasma enhanced ALD. And what we are seeing is that we don't need any wake-up cycles to wake it up. It is wake-up free device, and also we are getting better endurance for a wide range of temperature from room to elevated levels. This work was supported by Supreme, one of the 7 centers of SRC DARPA JUMP 2.0 program. With that, I would like to conclude my talk. Thank you.